Hello everyone, we are the Pick and Pie team and this is Abdel-rahman Wael, so let's get started. Have you ever thought about how they are arranged? Those red, yellow and green traffic lights with their unique timing for each square and street, those bumps and zebra crossing here and there, and even the number of lanes for each road across the city, how things work and how to make them more and more efficient. That is exactly what engineers are interested in. In fact, one of the most known problems that engineers have to deal with is traffic flow optimization. Over decades, as a result of the development that mankind has reached in industry, paired with the increasing population, the number of cars has been increasing and traffic problems have appeared. As you drive down the highway, suddenly countless rows of brake lights appear in front of you. A collision, a stop sign, a change in the posted speed limit, or a widening of the road are not present. So why is traffic so heavy? A phantom traffic jam occurs when traffic almost completely stops for no apparent reason. A traffic jam is an immediate phenomenon, meaning it behaves in a way that is more than the sum of its individual parts. But despite this, we can model these jams, even understand the principles that control them, and we are closer than you might think to stopping this kind of problem in the future. For a phantom traffic jam to form, there must be a lot of cars on the road. If all drivers keep the same constant speed and distance from other vehicles, it doesn't necessarily mean there are too many cars to travel across a stretch of road smoothly. It just takes a small disturbance to start the sequence of events that results in the traffic gridlock. In this steady moving traffic, let's say one driver slightly brakes. The next driver then applies the brakes a little harder, sending a wave of brake lights backwards through the traffic. These stop-and-go waves can travel along a highway for miles. With a low density of cars on the road, traffic flows smoothly, but small disturbances like individual cars changing lanes or slowing down at a curve are absorbed by other drivers' adjustments. But once the number of cars on the road exceeds a critical density, generally when cars are spaced less than 35 meters apart, the system's behavior changes dramatically. It begins to display dynamic instability, meaning small disturbances are amplified. Dynamic instability is not unique to phantom traffic jams. It's also in charge of other things like clouds, sand dunes, and precipitation. A positive feedback loop is the source of the instability. Any new vehicle reduces the number of cars traveling through a specific spot on the road per second after the critical density is reached. This causes an increase in vehicle density and prolongs the time it takes for a local pileup to leave a portion for the road, both of which contribute to stop-and-go traffic. Drivers frequently fail to anticipate the need to brake well in advance of a traffic jam, forcing them to apply more force to their brakes in order to prevent a collision. As a result, the wave braking from vehicle to vehicle is strengthened. What's more, drivers tend to accelerate too rapidly out of a slowdown, meaning they try to drive faster than the average flow of traffic downstream of them. Then they have to brake again, eventually producing another feedback loop that causes more stop-and-go traffic. In both cases, drivers make traffic worse simply because they don't have a good sense of the conditions ahead of them. Self-driving cars may be able to combat phantom traffic in real time if they are supplied with data on traffic conditions ahead via linked vehicles or roadside sensors. These vehicles would maintain a uniform speed, safety permitting, that matches the average speed of the overall flow, preventing traffic waves from forming. In situations where there is already a traffic wave, the automated vehicle would be able to anticipate it, braking sooner and more gradually than a human driver and reducing the strength of the wave. And it wouldn't take that many self-driving cars. In a recent experiment, one autonomous vehicle for every 20 human drivers was enough to dampen and prevent the traffic waves. Traffic jams are not only a daily annoyance, they are a major cause of fatalities, wasted resources, planet-threatening pollution, but new technology may help these patterns, rendering our roads safer, our daily commutes more efficient, and our air cleaner. And the next time you're stuck in traffic, it may help to remember that other drivers are not necessarily driving speedfully, but are simply unaware of road conditions ahead. drive accordingly. Now let's talk about our new piece of art, which is the game theory model. We've simply applied the game theory concept on our project. So those previous models were derived depending on the partial differential equations. They also depend on the existence of continuous road that has both starting and ending points. There would be no inlets or outlets and other conditions relevant to the road shape and the motion through it. And that is exactly the definition of the macroscopic traffic models, as they consider studying the road from a very far point. But the problem is that this is not the same as reality, so that's why we started taking the driver's decisions and behavior in the traffic network into consideration, as they have a great impact on the traffic network. And here comes the game theory concept, and took the job as a mathematical tool to study and analyze people's decisions in specific situations. And as it's a game, so we imagine that those people are in a game, and this game could be whether cooperative, so they are seeking the same goal, therefore helping each other, or competitive, therefore each one is seeking the best utility for himself through taking some decisions. So let's go and apply this concept on traffic network. The question is, what is the best utility in traffic? Simply, it's the shortest arriving time. Therefore, each driver makes his own decisions to achieve the best utility, such as increasing the speed, choosing shortcuts, overtaking, and this is what we are exactly studying. Now the questions that we are going to ask are, is the decision achieving best utility fixed? Thinking as if you are an expert driver taking the same road every day, does he drive the same shortcut or not? Through the same shortcut or not? And here comes the concept of the mixed strategy, which is that the best decision is variable, not fixed. So imagine if you are playing chess with someone, is it changing the holes to the right is the best decision? Of course not, as your decision is always changing, relying on your competitor's decision. And here traffic goes the same way. Every driver takes his own decision, thinking about other drivers' decision and how they would move to avoid being badly affected. So in time and with experience, driver starts taking his decisions more precisely to accomplish what's called the Nash equilibrium. And this is simply the game theory concept being applied on the traffic network. So this was all. Thanks for watching and hope you enjoyed it. Assalamu alaikum wa rahmatullahi wa barakatuh.